All right, so today we're going to introduce some new operations that are vector operations, but specifically designed to what we're doing. Now, remember, our ultimate goal here is moving along a path with a variable force. How much work do I get done from point A to point B? That's kind of where we're going for the next couple of weeks. So we're going to start with a couple of definitions. Put my pen here. The first one is called the divergence of a function f of x, y, z. Now, this is an operator, and it's actually the del operator. So if you remember from gradient, the del operator was the operator of partial derivatives. This is not a quantity. This says, I'm going to apply this to a function. So what we did before was, when we applied the del operator, we created the vector fx, fy, fz. So this operator applied to this function, I did this, 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 and created the vector. Okay, so that's what the gradient vector is. The del operator applied to a function. So now what I want to do is apply the del operator to a vector. So we're going to do it in a slightly different format. So now I'm not starting with a function, I'm starting with a vector. So if I start with vector, let's call it capital F, and that will be M and P, where each of these are functions of X, Y, and Z. So now what we're going to do is define something where we say it's del dotted with F, which seems kind of strange because this is not a quantity, but I'm going to dot it, which means that I'm going to take this, apply it to M, and like a dot product, I'm then going to add this applied to N, and then add this applied to P. This is a scalar valued function. This is no longer a vector. And this we call div f, divergence of f. We just abbreviate it div. So the divergence of f is the del operator technically dotted with my vector, or simply the sum of the three partial derivatives that I would create. This is an extremely simple process, but the most important part is my answer is not a vector. It's a function, a scalar valued function. So let's do an example of this. Okay, so if I've got this and I want divf, and that's how I write it. Okay, so what I'm going to do, I'm going to take the partial with respect to x of the first term. So that'd be 6xz plus the partial with respect to y of the second term. That would be 4x e to the y plus the partial with respect to z of the third term. And that's it. I don't set it equal to 0. I don't do anything with it. I just calculate it for now. This is at the very end of the course, basically the last lecture of the course. We'll learn how do we actually use divergence of a vector in a final answer. It turns out it's very, very important and it's huge in its use. But for right now, this is just a really simple calculation. Okay, so the divergence of a vector is a scalar valued function. Now the next one we're going to do is the more complicated. Now we're going to define something called the curl of a vector. Now the curl of a vector is another vector. And where this comes into play is with, well, the name curl kind of implies, you know, I'm going around something, I'm curling. The easiest way to think of where curl would fit in is if you think of a paddle wheel, like the old riverboats, the paddle wheel. Okay, it's going around in circles and it's generating a certain amount of force, and I'm creating work, but in a circular pattern. Now, all curls are not circular, but that's kind of where one of our first applications. But again, we're not going to use curl to find an answer so much till near the end of the course, but we're going to use it to do calculations along the way. So the curl basically is the del vector crossed with my original vector. Now, this is kind of a strange idea here. So if F, I'll put it down here. If F is, one more room. Okay, and del is I like stacking my vectors, then the curl of F is partial, I can't write today, partial of n with respect to x minus partial of m with respect to y in the first position, partial of m with respect to z minus the partial of p with respect to x in the second position, excuse me, and then the partial of n with respect to x minus the partial of m with respect to y. And I wrote this wrong. I'm sorry. It just dawned on me what I just did there. My bad. Sorry. Let me do that again. I'm standing too close to the board here. Sorry. In this case, I'm doing the first one. Sorry. I should have in the very first position. What should I have, folks? In the first one. We're doing cross product. Remember how we do that?
It should be the dp or the dy dp minus the dz.
Other way around. Other way. dp dy. Partial p.
Yeah.
So I'm standing so close to the board I can't even read my own writing. Minus nz. I prefer writing it in this form. By the way, it is absolutely correct to write it like this. And it doesn't even, it's not that it takes a long time. I think in this form it's just easier to conceptualize. I'm doing the partial of p with respect to y. And then the next one, of course, mz minus px, partials. And then the last one, nx minus my. My result is a vector. Unquestionably, my result is a vector. And nothing is off the table. Any vector you get is fair game for an answer, including the zero vector. In fact, the zero vector is a very, very important result that we'll find. So again, the curl, this is just a definition. Okay, we're not using it yet, but we will in a moment. So let's do a simple example. Let's say that our vector f about x squared y cubed sine of xyz and maybe e to the y squared z. I don't want it to be too complicated. That might look complicated, but remember, partial derivatives, I don't have any product rules to worry about. So now I want to do the curl of that. So when I want to do the curl, again, I like stacking. So somehow maybe just even above it, write what partials you're going to take. You don't have to do this, but I think it just makes it much easier to keep things in the proper order. So the curl of f is the partial with respect to y of this would be what? Anybody? The partial with respect to y, I'm leaving a space here.
2y e to the y squared z. Oh, 2yz.
2yz, good. Okay, minus partial of this with respect to z would be cosine, I should parentheses, cosine xyz times what? Partial with respect to z. This is a good exercise because we haven't done partials in a little while.
xy.
Times xy, good. And that's just my first component, okay? And then my second component, partial of z, that'd be 0. I'm going to write the 0 just so I know that I actually did it. And then over here, the partial with respect to x, 0. Okay, so I'm going to have a 0 in that position. I'll put it down here. And then the next one, partial with respect to x is going to be the cosine of xyz times with respect to x, should be yz. And then minus partial with respect to y. What's the partial with respect to y of that guy?
3x squared y squared.
3x squared y squared. And I got this big old ugly vector. I don't know what to do with it. But actually, it turns out the curl is a wonderful way of checking on certain things. Now I'm going to show you something. This probably the most important result of the day, and not a complicated result. Let's consider, sorry, I have to erase part of this. Let's consider that I've got a function. I've got a potential function. Okay, potential function of this. We now know that if f is the gradient of this, then that means that m equals the partial with respect to x, n equals the partial with respect to y, and p equals the partial with respect to z. Okay, that's that because m, n, and p are the three positions. If I started with a potential function and I took the gradient of that vector, this is my f, there's my m and p. Okay, big deal. I would like to find the curl of this vector. So the curl of this vector then, and again, all right, just small it by partial x, partial y, partial z. Okay, I always think it's a good idea to write, then you won't get out of order. So what is the curl of this particular f? The curl of a gradient vector. Well, let's see. So what I've got here is what? Obviously this is p, right? This is py, but since specifically that's already fz, then this would be fyz minus fyz. Oh, okay. And this would be fxz, because the order doesn't matter. And this would be fxz. I think you can see something here. This would be fxy, and this would be fxy. Anybody notice anything? What do I got?
0.
The zero vector, not the number, but the vector. Ah, so here's an absolute mathematical statement. First of all, the curl of a gradient vector is always the zero vector. But isn't the gradient vector our definition in this case? Because it came from the potential function, the gradient vector is conservative. This is one of the most important theorems in Calc 3. A vector is conservative if and only if its curl is the zero vector. So last day, I said, if I just gave you a random vector and asked, is it conservative? Did it come from a potential function? I said, that's not a trivial thing. If I start with the potential function and I ask for the gradient vector, that is a trivial thing. At this point in the course, nobody is challenged by that. If I start with a vector and say, did it come from a potential function? That working backwards is actually quite taxing. That's a major part of Thursday's lecture is how do I actually work backwards? But actually, there's no working backwards unless I actually know there's a potential function. If I just randomly made up 1,000 vectors without even thinking about it, it's very likely none of them are conservative. It's very likely none of them have a potential function. But how would I know? I take the curl of them. If the curl vector is the zero vector, then I can work backwards and find the potential function absolutely 100% of the time. There is no problem that you can't work backwards and find the potential function if your vector is conservative. If your vector is not conservative, the potential function doesn't exist. So there's no point in working backwards. And the easiest test is to do the curl. So this is kind of a nice little feature. So the curl of a conservative vector must be the zero vector. Again, that's how you can tell. Plus, it's also an easy way to test. You see, when I'm doing my curl, I just did my curl a moment ago. Is it possible I made a mistake? Is it possible I made a mistake in finding my curl vector? Yeah, there's always a possibility I made a mistake. So if I have a vector that I know must be conservative and I take the curl and I don't get the zero vector, then I know I've got an error. It's a nice little check. Okay, so let's see. I want to try another one. How about,
Professor,
oh, yes.
what's conservative vector? I'm kind of confused.
A conservative vector is one that comes from a potential function. That's the definition. That was last day's lecture.
Oh,
Starting with any function, if I create a vector by taking the gradient of that function, that vector is conservative. That's the definition of a conservative vector. That's it. Now, does it have use in actual application? Oh yeah, conservative vectors are the most important types of vectors, but that's later. That's way in the future. That's Thursday's lecture. We're going to use conservative vectors to answer questions. Okay, so we have to, first of all, what is a conservative vector and how do I test it? Today is how do I test a vector to see if it's conservative? So let's try another one. Okay, how about, how's this? Determine if the vector, how about, if, I'm sorry, give it a name. All right, let's all take a moment. I want you to determine if this vector is conservative. This should be a fairly simple process. So in order to determine if this vector is conservative, we need to take the curl. So everyone try that just for a moment, see what we get.
Professor, I don't want to be that student, but you were moving a billion million hours per second, and I have no idea what you did for the curl of f.
Well, the curl is a definition, so it's del crossed. So basically, you're going to go partial with respect to y minus partial with respect to z, then partial with respect to z minus partial with respect to x, then partial with respect to x minus partial with respect to y. That's if you don't put the letters up there. That gives you things in the right order. I said put the little symbols above it. Makes it a little bit easier to keep track of. So let's go through this. The partial, I'm doing the cross, so it's that. And what will that be?
X squared minus x squared.
So it'll be x squared minus x squared. And by the way, don't start rejoicing and say, I got a 0. I might not get 0 in either of the other two positions. Just because you have a 0 doesn't mean they're all 0. In fact, I will purposely trick you on occasion and give you somewhere. Some are 0 and not all are 0. That's not that hard to do. So this partial respect to z is
xy minus 2xy.
so 2xy, and then minus 2xy, and then finally the partial with respect to x, that'd be 2x, sorry, can't write, 2xz, and then with respect to y, minus 2xz. There's much rejoicing. The vector, this vector is conservative because the curl is the 0 vector. Now, this is where you got to be really careful, because if I made any arithmetic error, and what's the hardest ones to check are ones with sines and cosines and things, because of the pluses and minuses that I might make mistakes on. So if there's sines and cosines and I make a plus minus type of error, I may conclude conservative when it's not. I may conclude not conservative when it is. So you just got to be a little bit careful. But physically taking a curl should be something that's relatively simple. That, again, that's not something I expect anybody to labor with. All right. Now we've defined those. Now we're going to move on. Now the kind of the whole point of this chapter is the next thing, or at least a great portion of this chapter, and what are called line integrals, which is the great oxymoron, because first of all, we're never going to be dealing with lines. We might be dealing with line segments, but you're never going to deal with a line. A line is infinite and has nothing to do with anything being straight. So why they're called line integrals, I don't know. It should be finite curve integrals. So here's the idea. And my examples I'm going to do primarily in 2 dimensions, so I can draw them, but the rules are the same in 2 and 3 in terms of how we do the calculation. So I'm starting here, I'm moving through space, I get to here. Okay, so let's just say that's x0, y0, and that's x1, y1. I'm going from point A to point B, I'm going in this orientation, and I am applying a certain force. So you'd have to have something to, an actual force, probably a variable force. So the question really is, how much work do I get done along the path? So a line integral means you're integrating along a path. You're not integrating over a region. You're not integrating over a surface. You're not integrating over a volume. Those things will come. But right now we're integrating over a path. So the example I gave you was, you're pushing a wheelbarrow across campus, up and down hills, how much work did you get done? Particularly if the force is not constant. See, if the force were constant, all I would have to do is find the length of the curve and then multiply it by the magnitude of the force. That would be really, really simple. It's never going to be like that. So how do I do this, and what does a line integral actually look like? Well, there's actually 3 forms. Again, I'm going to do the 2-dimensional problems because when we move into 3, it doesn't change how we do it. It just changes the number of variables. Think of it like partial derivatives. If I had 2 independent variables versus 3 independent variables, partial derivatives don't become harder with more independent variables. I just have to take more derivatives. So there's 3 ways the integral can be asked. I can have f of xy, this is a single integral, mind you, dx. I can have f of xy dy, and I can have f of xy ds. And that's tricky. This means I'm integrating it in the x along the x only. This means I'm integrating it y only. What is ds? Anybody want to take a shot? What is s? Well, what do we always use s for?
Surface area?
No, that technically we'd use capital. Little s is typically always what?
Arc length?
Arc length.
Yeah.
So this means we'd be integrating it along the arc length, which kind of means we're combining x's and y's together. This is algebraically, this is the ickiest of the bunch. So if this and this are actually relatively simple, and I'm going to demonstrate all 3 in a moment. Okay. But one is I'm integrating it only with respect to x, one is only with respect to y, the other is along the arc, which means I'm integrating with respect to both. So let's remind ourselves that ds dt, do you remember what that is? That's dx dt squared plus dy dt squared under the square root. And if you want, think of it as speed also, because we know that arc length and speed, right, have to do with each other. Okay. So if this is true, and then I integrate both with respect to t, then what we do is we say ds is the arc length parameter dt. Oh, kind of like when we do a u substitution, right? We say u equals and then du equals something dx. Very much similar. ds is something dt. That means that I never actually have an x and a y. So common sense would dictate, if I'm asking you to calculate, let's say something like a work, my answer is going to be a scalar. My answer is not a function. My answer is a value, probably units, but for now, my answer is a value. If I integrated a function of 2 variables, but only with respect to 1 variable, think about that for a moment. If I integrated a function of 2 variables, but with respect to only 1 variable, then I should still get a functional answer. Oh, I want a scalar answer. So that means that I'm going to have to parameterize. I'm going to have to treat both x and y as functions of t. Then I would make this an integral dt, dt, dt. So that's how we actually will integrate the thing. The other notation we put then is I put a little c at the bottom. C means along a particular curve. C refers to the specific path that you will have in that particular problem. Okay, so we will always define a path. So I'm going to do a fairly simple example here. All of this stuff here. So let's suppose that our path I'll keep it really simple. Our path, we're going to use let's say, how about a quarter of a circle? So our path will be, now what's interesting is the orientation. Whenever you're doing a path, the orientation, you could make it whatever you want, but whenever you're doing something like in a trig-ish situation, because you're clearly, I'm going to have sines and cosines, we typically will do our path in increasing angles. So I generally do my path in this direction. So let's say this is x squared plus y squared equals, I don't know, how about 36. So my circle was this. So I'm going to let x equal cos t. I'm going to let y equal sine t. Well, almost correct. 36. How does that get figured into here? Think Calc 2. If I'm parameterizing along a circle, well, think polar. Isn't x and y both r cosine, r sine? So what should go here?
6.
6. Oh, okay. Now when I do x squared plus y squared, yep, okay. If I forget the 6, then I'm only doing a circle of radius 1. And then the last part of this is t will range from what to what?
Zero to pi over 4.
0 to
Pi over 2.
pi over 2. Yeah, quarter circle. Okay, so that's going to be, this is my path, and I'll write it like this. Okay, so I'm going from here to here. So ultimately, I'm going to integrate something with respect to t. So now here's what I want to find. I want to find each of the following. I want to find, how about, let's keep the integrand really simple. How about we keep the integrand, I don't want it to be complicated. How about just x, do dx, x dy, and x ds. How's that? I want to do these three integrals. I could have picked any integrand. I want it to be something really small and simple. We're going to do 3 different problems. Okay, and I don't expect to get the same answer. So let's do this one first. So what we want to do is, we're always going to do a parameterization, but the parameterization is never dependent on the integrand. Now, when we do polar and we do spherical and we do cylindrical, the integrand plays a huge role, because if my integrand, let's say, is, x squared plus y squared under a square root, okay, I'm probably going to go polar or cylindrical because I can, change that to r's. The difference is, in a line integral, your parameterization only depends on the path. It has nothing to do with the integrand. So this is the parameterization we chose to describe this path. So I will now apply this parameterization to all 3 integrals. So does that make sense? So that's how we would work this. So in the first case, clearly x is 6 cos t. What's dx? Anybody? If x is 6 cos t, then dx is
6 sine, minus 6 sine t.
negative 6 sine t dt. So this first integral, I'll write them, we'll do them one at a time. I don't have room to do them all. This first integral will be 6 cos t times negative 6 sine t dt from 0 to pi over 2. And when you're looking at that, you're going, oh, that's not that complicated. So let's continue. So that would be negative 36 cos t sine t, or sine t cos t. I'm going to write it sine t cos t. If my u is sine t, then clearly my du is cos t. That makes this really easy, doesn't it? So if my u is sine t, then my du is cos t. So this is u du. So my answer is 1/2 u squared. And that's my answer. So sine of pi over 2 is 1. So sine squared is 1. Sine of 0 is 0. So my answer is just negative 18. Okay. Nothing special about it. That's my answer. So I'm going to write it right here. I'm going to do that because I need to erase everything. So that was our first line integral. It just wasn't that bad. Now let's do the second one. So now with the same x, now I need dy. Now remember, this was our parameterization. So what's dy? Anyone? What's dy?
6 cosine t.
Yeah, 6 cos t dt. So my integral x dy is going to be the product of these two. So that will be 36 cos squared t dt from 0 to pi over 2. Now, we don't love sine squared and cos squared because it means I have to use a double angle formula. So just to remind you, right, cos squared t is 1/2 of 1 plus cosine of 2t. Right, that's the double angle formula in reverse. So I need to replace this with this because otherwise I can't integrate it. So I'm going to have 18 times the integral from 0 to pi over 2 of 1 plus the cosine of 2t. Okay. I mean, it's not our favorite, but that's just not that hard either. So that's 18 times t plus sine of 2t times 1/2. Okay, remember, if I differentiate, boom, I get that back again. From 0 to pi over 2. Now, when I do the sine of 2 times pi over 2, that's the sine of pi, which is 0, minus the sine of 0, which is 0. So this term doesn't actually contribute. So I'm going to get t evaluated at pi over 2 only times 18. That's 9 pi. Wow, that's pretty different from my first answer. So that's 9 pi. Now let's do the last one. Now the last one is the most work. And in fact, in general, strangely enough, it is often the case that you can only state the integral when it's a ds. You can't always find the integral because the ds itself involves the square root of a sum of squares. And that might be something that I can't work with easily. This one we will be able to because the circular parameterization pretty much always makes things easy. All right, so now that's my x. Okay, what is ds? Well, ds, we just did a moment ago. What is dx dt? That was -6 sine t, and I'm going to square it. What was dy dt? We just did that. That's 6 cos t, and I'm going to square it. All under the square root dt. We just did this a little while ago. Okay, I explained where that comes from. Well, this is 36 sine squared t plus 36 cos squared t under the square root. What's 36 sine squared plus 36 cos squared?
36.
36. And the square root. So this is just 6 dt. I'm liking this one. See, this one's very friendly. So if I have circular parameterization, then the ds is easy. If I have something different, right? We know this when we were doing the normal and tangential components, remember? We took simple functions and we found out, oh my God, it was horrible when we calculated curvature and all the other things because of all the square roots involved. But when it was sines and cosines, all of those things were really, really easy. We love sines and cosines in this case. So the last integral is the integral again from 0 to pi over 2, 6 cos t times 6. And that's just 36 sine t from 0 to pi over 2, which would be just 36. So I chose 3 really, really simple integrals just to illustrate that we got 3 different answers. I mean, it's mathematically possible that any 2 of these could have been the same. It would be really hard for me to design a problem where they're all 3 the same, but everything is fair game when you're doing a line integral. Now, this is the first and the lowest level. This is not how it's always going to look now. Now there's 2 different situations I want to discuss. Okay. The first one is the way a line integral is typically going to look, whether it's 2 or 3 dimensions, is the line integral will often look like this. I have the integral over the path of something of the following form. And it's when I write m, it's understood it's a function of x, y, or x, y, and z. X and y if I'm in 2 dimensions, x, y, and z if I'm in 3. This is the most common form, or if I'm in 3D, it's this. If I'm in 2D, it's this. And both are fair game. This is the most common form a line integral takes. You say, wait a minute, what do I do? Do I break this up into 3 separate integrals? No, you do one integral, but you parameterize along your curve. In other words, when I perform this integration or this integration, just like in the last example, I'm going to do integrals of t. Because when I do my parameterization, x is a function of t, y is a function of t, and perhaps even z is a function of t, then dx, dy, dz all are something dt. So then I end up doing this. Again, this is probably the most common form we will deal with. And that m, n, and p are the same m, n, and p that we saw in the force vector. So there must be something going on here. You got to tune in on Thursday. That's really Thursday's lecture. So if I gave an integral in this form, okay, so let's try something like that. The ds is the least common of the 3. Okay, so let's suppose, I said, let's calculate the following. I'm going to keep this relatively simple. Let's say it's 2x dx plus, I don't know, y squared dy. And my path is, how about 0, 0 to 9, 3 along the path y equals the square root of x. Okay, so my path, I'm going from here to here. There's my path. I want to perform this integration along this path. Now, I've got y equals square root of x, but when I start taking derivatives, that can be kind of icky. Could I make this x equal y squared? Would that be legal, do you think? Does it change anything if I write it that way? Anybody? I'm going from here to here. Will this change anything if I write it this way versus the first way?
Yeah, shouldn't it give you to the bottom below, above and below the y-axis? Oh,
I'm not using that part though, so I'm only using this part. So would they be the same?
Yeah.
Yeah, and I think most of us would agree. I'd rather do this guy's derivatives. It might be a little bit easier than the other guy's derivatives. It won't change your answer. You'll always get the same answer, but the algebra, when I'm doing dx and dy using this one, might be a little ickier. That's all. So you always have license to do this. And the other thing you can do is you can say, all right, well, either way, it doesn't matter which way I look at it. So in other words, if I wrote it this way, and you said let x equal t, then y is the square root of t. That's a harder parameterization. But if I write it this way and I say, oh, let's call y equal t, then x equals t squared. That's an easier parameterization. That's why I'm saying I can look at it either way, but I'm still going to parameterize. But if I look at it this way, I don't really want the square root in my parameterization. It's not wrong. It just makes the algebra ickier. So now I'm going to parameterize. So I'm going to say, let y equal t, then x is t squared. And I could have done that here. It's just less obvious. Then dy is 1 dt. Dx is 2t dt. Okay, everybody got that? So when I go to this integral here, that's what I'm going to replace everything with. Okay, so I'm going to go ahead and erase this picture. So this will become the integral. Oh, by the way, last part, very important. Almost forgot. What is the range of values on t? I only have 2 choices, right? It's either 0 to 9 or it's 0 to 3. Which is it? Which one is it? We're
0 to
using
3.
y equals t. So it's got to be 0 to 3 because y is our t. So in other words, y is ranging from 0 to 3, and we chose y to be the t. We could have done it the other way, but this is an easier parameterization. So this is 0 to 3. I've just indicated you the first common error is to choose the wrong value for your t. Now, what's going to go here? 2 times x times y times dx, which is 2t dt. But I'm going to put the dt at the end because the y also has a dt, plus y squared, and then dt. Technically, it's quantity dt plus quantity dt, which is kind of redundant because it's all dt. So I just put the 1 dt at the end. Less writing. Now, can I clean this up a little bit? 2t squared t, 2t, that would be what? 4t to the 4th plus t squared dt. This scary looking problem here becomes this really simple single integral right here. That's usually what happens is you end up with something not terribly taxing. So 0 to 3. So what do we got here? So we got 243 times 4, so it's at 972 fifths plus 9, or what, 1017 fifths. Okay. Does that answer mean anything to us right now? Well, not yet. But later on, if we're in a physics class, you're doing this problem, you're probably putting, newtons or something, some unit of force. I'm sorry, not newtons, joules or something, some unit of work. I'm not worried about that right now. We're not doing anything unit related because we haven't technically defined this as work. It's work. Okay, the textbooks won't even define it as work for a little while. It's work. It can't be anything else. You're integrating force over a distance. So your units have to be force times distance. Yeah, it's always work. That's all of what we're doing, it's the mathematics of work in general. It's the work of work, if you will. Okay, so that wasn't too terrible. Okay, parameterization is usually easy. Where this gets just a little bit tricky, and I'm going to keep the problems, by the way, I'm going to keep them really simple in nature. All right, we're going to do a similar problem. All right, let's say we want to integrate, I want to keep this fairly simple. So we have xy dx minus 3, about 3y dy. Again, I want to keep this really, really easy. And here's our path. I'll draw a picture of it. Our path is from the origin, we're going to move along the x-axis to the point 4, 0. Then we're going to go straight up to the point 4, 8. Then we're going to go down diagonally, how about to the point 2, 6. Okay, we'll call this C1, C2, C3. I want the work done along this path. So I want to do this integral along that path. Ooh, that's kind of tricky, isn't it? So how do what is this? This means that C equals C1 union C2 union C3. That's the first way we write it. So my final answer is going to be the sum of 3 completely separate and independent integrals. I do 3 completely different problems, one at a time, each with their own unique parameterization. There is no such thing as a one-size-fits-all when I have multiple paths. Okay, so I have multiple paths. So let's do it one at a time. So along C1, all right, well, what is my equation along C1? So I'll write that over here because I'm gonna have to rewrite things. C1 is what path? I'm going from 0, 0 to 4, 0. So I'm doing a horizontal line. So isn't the equation of a horizontal line, isn't it y equal a constant? Everybody, isn't that what it is? So on C1, I have y equals 0. Okay. And what is x? X would be t. Y is 0, x is t. dy is 0 dt. Dx is 1 dt. X is changing, that's why x is t. And finally, what does t range from? T ranges from 0 to 4. I started at 0, 0, I ended at 4, 0, 0, x was changing. Okay, so this is my parameterization for the first integral. So along C1, I'd have t times 0 times 1 dt minus 3 times 0 times 0 dt, oh, an extra 0, if you will, dt. And this integral clearly is going to equal what? 0. Okay, that one wasn't very exciting, but it was 0. It wasn't 0 because of my path. It was 0 because of my integrand. Okay, the path can't make it be 0, only the integrand can. So along C1, this was the only parameterization that made any sense. So now what about C2? Now I'm going from 4, 0 to 8, 0. I'm moving vertically along the line x equal 4. But y is changing, so this time y will equal t. Okay. Dx is 0 dt. Dy is 1 dt. And t will range from 0 to 8. Okay, so my second integral, I'll use a different color here. So now my second integral is 4t, oh, but that was 0 to t, minus 3t 1 dt. And oh, I'm sorry, I don't need this. I forgot to put the limits on the first one. My bad. The limits on the first one, that should have just been 0 to 4 because we already did this. So these limits are 0 to 8. All right, so let me erase this. We already have that. So this is the integral, if you will, of just negative 3t. So this will equal negative 3 halves t squared from 0 to 8, which would be negative 96. Okay, now we have one more path, C3. Now C3 is going to be the trickiest one, not because of the shape, but because it feels like I'm going sort of backward. So when I set up my path for C3, well, that has a slope of 1, clearly. So it doesn't matter if I choose x to be t or y to be t, but in xy world, let's kind of figure out the equation of this line, if we will. If this line kept going, I think it would intersect at 0, 4. Do a little quick check here. So the line is the line y equals x plus 4, I believe. So what would be an easier parameterization? Picking x to be the t or picking y to be the t, or does it make any difference whatsoever? Anybody?
Probably doesn't make much difference.
It doesn't make much difference, but if I wrote my equation this way, then picking x to be t means then y is just t plus 4. I don't have to think. If I make y t, then I got to rearrange, and it doesn't make any difference. But if I'm going to think of my line in xy world looking like this, then I think picking x to be t and then y to be t plus 4 makes more sense. Then dx equals 1 dt, dy equals 1 dt, and t, we said x is t. So I'm looking at the 2 and the 4. Okay. But I said this one's the trickiest one. Anybody want to guess why this is the trickiest one? You can't be wrong, just you're guessing. So along C3, my integral should look like xy, so t plus 4 times 1 dt minus 3y 1 dt, and then my limits of integration, of course, are what to what? Anybody want to try that one? What are my limits? From what to what?
8 to 6.
I'm sorry, from what to what?
8 to 6.
Well, remember we picked
Oh, yeah, like from 4 to 2.
4 to 2. Why not 2 to 4? Why 4 to 2? You're correct. That's why I said it's tricky. Why is it 4 to 2? Because I'm starting here and I'm ending here. Everybody got that? If I said 2 to 4, that would mean I'm going in the other direction, and direction does matter. Direction matters because we do have vectors. Oh, and a simple analogy, if I'm, pushing in this direction, then how much work did I get done in this direction? Well, that's easy. But if I'm pushing in this direction, how much work did I get done in the opposite direction would be the opposite sign. Oh, because direction matters. So this is the tricky part. I'm going against the grain, so I have to reverse those because my x started at 4 and it ended at 2. Okay, so with that said, this is not difficult, but I don't want to mess it up. So this would be t squared plus 4t minus 3t minus 12. So my integration looks like t squared plus t minus 12, which would be a third t cubed plus a half t squared minus 12t, 4 to 2. So at 2, we'd get what, 8 thirds plus 2 minus 24. And then at 4, we'd get 64 thirds plus 8 minus 48. Now I'm gonna be lazy to use my calculator this time. So I've got 8 thirds. I tend to have less faith in the calculator answer. Interesting. I got negative 2 thirds. Okay. Yep, that looks right. So now my final answer. Remember, we said the answer was going to be the sum of the 3 integrals. So our answer is going to be 0. What was our second integral again? I erased it. Anybody?
Minus 98.
90, was it 96?
Negative 96.
Okay, negative 96. My 6 wasn't that bad, was it? Minus 2 thirds. So that'd be what? Negative 290 thirds. I got a negative answer. Can you have negative work? Does that make sense? Can work be negative or 0? That's a tricky one.
Because it's a vector, isn't it?
Because it's vectors involved. The way if you guys have been in my calc classes when I've described this physically, Ian, you may have been back in the day before we all got sent home. When I talk about work, and I say I'm pushing the refrigerator across the room. The refrigerator has a certain amount of weight, and I'm pushing a certain distance. So if I say how much work got done, you just multiply the weight times the distance. That's easy. Now I want to push it across the room, but I ended up going off at some angle. So there's an angle between where I wanted to go and where I actually went. So I push it the same distance, but at an angle. So how much work did I get done pushing across the room? Well, now I got to do a projection. So if I wanted to go 50 feet and I went 50 feet at a 45-degree angle, then I only went about 35 feet in the direction I want to go. Oh, there's a cosine of theta in there, right? So now I take my magnitude of force multiplied by my distance times my cosine of theta, right? I want to push the refrigerator across the room. I know that's difficult in 2 dimensions, seeing my perspective, but I end up going sideways 50 feet. So I'm going this way when I'm pushing that way. I can't move it forward. So how much work did I get done when I moved it 50 feet sideways? I got 0 because I got 0 in the direction I wanted to go. I went completely sideways. So now I'm getting ready to push it up a hill. So I unlock the wheels and it starts rolling backwards on me and I stop it after I roll backwards 50 feet. How much work did I get done going forward? I got a very large negative amount of work done. How come? Because I was going this way, I ended up going backwards. And the easiest way to justify this is I now have to do a large positive amount of work just to get it back to the starting point. So yes, I can have negative work. If my force is in the opposite direction as which way I'm trying to go. So like, with the springs and things like that, I wanted to go this way, I ended up going that way. My force and my directions were opposite. Of course, I'm going to get a negative value. Why? Because the angle between them was 180 degrees and the cosine of that is -1. So in general, if the angle you end up with between the direction and the force is obtuse, then you get a negative amount of work. If it's a right angle, you get 0 work. Now we know this from earlier. This isn't new information. And I'm pointing that out because when I got this answer, all that means is in this process, I would have to do a positive amount of work to get back to the starting point. Now, the 0 work is kind of a tricky one. Now, this is something that's going to be a huge concept over the next week or two, but this has to do with conservative vectors. And I'll give you a hint. It's the trick question. All right. So Ian's going to go on a trip. He's going to go across country. So he's going to leave San Diego and he's going to chart it very carefully. He's going to go to the, New England or whatever. And he's going to drive and then he's going to drive back. And so he figures out he makes the trip exactly 6,000 miles. It takes him exactly 100 hours of driving. Trying to keep the numbers simple. So he leaves from his house, he drives exactly 6,000 miles and he gets home. Took him exactly 100 hours of driving. So what's his average velocity? His average velocity? Anybody?
Would be 0.
Close. It'd be the 0 vector. But his average speed was 60 miles an hour. You're right. The average speed was 60 miles an hour. So why is because your displacement was 0. When you end where you started, your displacement is 0. And I'm going to give you the most important thing you'll ever learn in a calculus class the rest of your life. When the displacement is 0 and your vector is conservative, the work is always 0. If the vector is not conservative, the work can't be 0. So we really like conservative vectors. In physics, it's called conservation of
energy.
0. None's gained, none's lost. This is the part of the class, and again, I'm not going to go into the units. Don't worry, I'm not going to kill you with that. But this is the part of the class that the physics people say is the most important, because this explains all of the rules of physics from a calculus perspective. A conservative vector, the beautiful thing about a conservative vector is if the loop is closed, your integral is going to be 0. We're going to prove that, by the way. That's a major theory next week. We're going to prove that, and then we're going to use that fact to do the, technically speaking, the fundamental theorem of calculus is considered the most important result in the world of calculus and probably the world of math and science. But a very close second is what we're going to do a week from today, something called Green's theorem. A lot of people say, no, that's on a par with fundamental theorem in terms of its importance. And we're going to be using all of these facts in there. And the idea is we're going to make complicated processes much, much simpler. And I'll give you a hint. The way we're going to make them simpler is by closing the loop. If I close this and make it a closed loop, there's certain things I can do, whether it's conservative or not, that will make my life significantly easier. This problem was nasty because I had to do 3 integrals. I'd rather only do 1, but that's coming. All right. So that's what we're doing for today.